Hello and welcome to this module 24 of manufacturing systems technology. Quick recap of what we did in the last lecture. We started analyzing a problem where we wanted to estimate the optimum tool life and optimum cutting speed for both the conditions, that is minimum cost per piece and maximum production rate per piece model, and we further found out the conditions subjected to the fact that the tool can be ground for about 5 times before it is finally discarded. So we were using one cutting edge of the tool for about 6 times. The original cost of the tool was recorded as $27.96 and the total grinding time was given as 2 minutes, a tool changing time of about 0.250 minutes, and workpiece loading unloading time to be again 0.50 minutes per piece. So we obtained actually the values for the optimum tool life or optimum cutting speed for both the conditions. The V min for the minimum cost model came out to be about 82.337 meter per minute, and the T min, the total tool life for the minimum cost model, came out to be about close to 84.56 minutes, and similarly the V max for the maximum production rate model was intuitively what it should be, about double in this particular case, and the T max, the maximum tool life model, in that particular case came out to be close to about 2 minutes, okay. So which is about a 40th from the T min. So the way that we calculated these different parameters seem to be justified or logical. The next step was obviously to calculate the minimum cost per component or time per component or even the corresponding lead time, and then also the maximum production rate and corresponding cost per component and the lead time in both the models. So we want to do that now. So here let us say the first goal is to calculate the minimum cost per component and the time per component corresponding to the minimum production minimum cost per unit model and lead time. So what we first do is to try to find out what is the actual cutting time in this particular case, the TC value, which can be represented as PL or pi LD divided by 1000 V, and this is because of the minimum cost. So we use the velocity condition corresponding to the minimum cost model times of the feed F, and so in this particular case it comes out to be 3.14 times of the length of the piece, which is about 300 mm, the total diameter, which is about 60 mm, divided by the velocity minimum in terms of meters per minute. So that is why this 1000 factor comes into picture, 82.337 meters per minute times of the total amount of feed. In this case it is 0.20 millimeters, okay. So that is how the optimum tool life equation has been designed. Remember, the V min is always, or the velocity is always in meters per minute in this particular tool life. The reason why, in order to convert this into millimeter, this 1000 factor comes in automatically in the tool life equation, I mean in the cutting time equation. So this comes out to be roughly about 3.43 minutes, okay, if you are considering the minimum cost per component model, and from this you can have an estimate of what time will it be needed for what would be the cost per component which will come out in this particular case, or what would be the time per component which will come out, or as a matter of fact what will be the lead time. So let us talk about the cost first. So Cu, the cost per component in this case, is actually equal to the I would say, if you look at into the Cu equation earlier which we had done for calculating the cost, the minimum cost, we had a variety of things here which included C0 T1 plus C0 times of pi LD by 1000 Vf, remember that is how we derived the cost model, plus C0 times of VLD divided by 1000 Vf times of V by C 1 by N times of TD plus C1 times of pi LD divided by 1000 Vf times of V by C 1 by N. So this is how the cost per component was supposed to be, and the C0 was earlier estimated, if you may remember, to be 0.25 dollars, quarter of a dollar per minute, just in the last problem or last part of the problem. So we can use this value here right away. T1, if you may remember, is actually the total non-productive time. And if we really go back to the question, we have the total non-productive time as mostly the tool changing time, sorry, the workpiece loading unloading time, I am sorry, and that comes out to be roughly 0.50 minutes per piece. So that is how this is the time during which it is not really contributing to the actual machining, but it is an essential evil, it has to be there. So it is a non-productive time that is getting added here. So here therefore the final cost equation per component Cu comes out to be equal to 0.25 per minute times of T1, which in this case, in this particular case, is 0.50 plus again if you look at the condition corresponding to the minimum cost model, V gets replaced by V minimum in all the places in the equation where V has been reflected, and if we add these, or if we just replace these values in this particular setup, we have the next term here as 0.25 times of this whole term, which has earlier come out to be 3.43 minutes, okay, the total cutting time. So 3.43 plus again 0.25 C0 times of 3.43 times of V minimum by C. In this particular case, the V minimum by C value to the power of 1 by N is actually nothing but sort of 1 by time minimum. Time minimum is 3 point, you have already calculated it to be in particular value here as 84.56 minutes. So we replace this by 1 divided by 84.56. Okay, again just coming back to this paradigm here, you know that V minimum times of T minimum to the power of NSC. So here essentially what we are trying to do is to find out what is T minimum, which is you can say C by V minimum to the power of 1 by N. So if I do 1 by T min, this becomes equal to V minimum by C to the power of 1 by N, which is nothing but this particular value right here. Okay. So we are just substituting this by 1 by T minimum. T minimum has already been calculated for the minimum cost model earlier, okay, derived earlier, times of TD. TD obviously is the time to change a cutting edge in minutes. This we had actually represented in the one of the earlier lectures, how TD is coming into this equation. And so if we look back into the question, the time to change a tool in this particular case given here for example is 0.50 minutes. So therefore the tool changing time in this particular case, as you can see right here, is 0.50 minutes, and that we want to just plug in here as TD as 0.50 minutes, plus obviously the C1 value, which again was earlier found out if you may remember in the optimum cost model or as the total amount of tooling cost which was $5.16. So, C1 actually was calculated to be $5.16. If we just go back into a few modules and see, there is a way we assumed that there are 6 times that a tool can be used with a new edge and then grinding it 5 subsequent times, and we accounted for the tooling cost per cycle of that 6 cycles, and also we accounted for the labor and overhead charges per cycle times of the total amount of grinding time that would take for one edge, and that way per cycle we could estimate this particular cost of $5.16. So, this C1 is now substituted here. So, we in place of C1 here, so we have $5.16 times of the TC value because of the minimum velocity condition, which again was calculated to be 3.43 as earlier, times of V minimum by C in the same manner to the power of 1 by n, which from the previous term here happens to be 1 by 84.56 minutes. So, that actually comes out to be the cost per component in the minimum production model, or if you just calculate that, the total value sums up to be $1.197 per piece. So, that is the minimum cost that can come out, and the velocity optimum that is obtained for this minimum cost condition is about 82.33 meters per minute, and the minimum time that is needed, that is a tool lifetime that one particular tool can be utilized, is about close to 84.56 minutes. So, it is pretty high, and that results in the minimum cost per piece. Obviously, this is one kind of business situation where you really are cost driven. The other can be mostly related to the maximum production rate driven, which we will do in the subsequent analysis. So, here the production time per piece, assuming that you have a minimum cost per piece which has come out, the production time per piece can be TU. So, this can be represented as T1, the total amount of time needed for loading unloading, the unproductive time, plus the actual cutting time considering the minimum cost optimized velocity condition, plus the time to replace or do edge replacements, etc., which is actually the cutting time times of 1 by T minimum So, if this is the total cutting time per for a particular situation, and this is the inverse of the total lifetime for the minimum cost condition, then cutting time by minimum tool life would actually represent the number of times or the frequency at which you can replace the tool, and this multiplied by TD, which is actually the total tool changing time which is needed. So, you are basically changing at this frequency TC by T, TC by capital T, and multiply that with TD, and the TD value here has earlier been obtained as 0.50. Okay. So, that is how you actually do the time per component corresponding to the minimum cost model, and this obviously just substituting the values here, this is 0.50, this comes out to be 3.4325 from earlier equation. Let us just assume 3.43, not detailed calculations. Then you have again 3.43 times of 1 by T min, which is 84.56 as you have seen here, times of 0.50, and this amounts to a total time of 3.95 minutes per component. Okay. So, we now have two different values corresponding to the minimum cost model, where we see that the per component production time or the machining time is close to about 4 minutes, and it costs about $1.2 per piece in the minimum cost condition. So, we can also try to find out or try to figure out the lead time for the whole batch. So we have about 500 units that we need to produce here. So the lead time is, as you know, involves the major setup time and then also reflects the time per component times of the batch size here. The Q is 500, the batch size we are using is 500. Assume this to be negligible because it's not mentioned in the question. So we have per component 3.95 minutes times of 500 as the total lead time for this whole batch to get processed. In this condition it's about 1976.4 minutes, okay. So corresponding to about close to 30 hours or so. So that's how you actually calculate the cost per component, the time of production per component and the lead time as regards the minimum cost model or minimum cost per component model. I would also like to go further ahead and try to explain to you the condition, the same parameters for the maximum production rate model. So this is part 4th of the question. You considering maximum production rate model and you are willing to find out here the cost per component, obviously the time of production per component and the lead time. In this particular case obviously we want to consider a cutting time Tc by substituting the value of V to be V max as derived in earlier equation, and this is 3.14 times of 300 times of 60 divided by 1000 times of 174.11. Remember this is the maximum velocity condition corresponding to the maximum production rate, the optimum velocity, times of 0.20 which is the feed here, and this comes out to be 1.623 minutes, okay. So that's how small it is. If you just compare this with respect to the earlier cutting time, it was taking a hell lot of difference. It was like almost twice in comparison to, obviously because here the velocity is much slower, and you can see here the minimum velocity here is 82.337. So the maximum cutting time was recorded as 3.43 in that particular case. Here it is about half of that value because obviously the velocity is quite different, about 2 times in this particular case. So the time of machining should change to almost half. Now the production time per piece at the tool velocity Vmax can be recorded as the unproductive time plus obviously the cutting time Tc. In this case you can substitute Vmax times F plus the total tool changing time. In this case let us say we assume this to be the total cutting time for the maximum production rate condition divided by the maximum tool life Tmax. So this gives you an idea of the frequency of change that is needed as regards the workpiece times the Td, which is the changing time, the tool changing time per cutting edge, you know, which has been earlier given as 0.50. So here if I just substitute all the values 0.50 plus this becomes 1.623 minutes plus 1.623 times of Vmax by C. In this case as you know this is about again 1 by Tmax, and Tmax was earlier calculated to be something like 2 minutes. So I have this recorded directly by 2 times of Td. In this case Td is actually about close to 0.50. So the total time per component comes out to be 2.52 minutes. Remember the earlier time per component was quite higher. In this particular case it came out to be about 3.95 minutes. Here this comes out to be about 2.52 minutes per component, obviously because the production rate is at its maximum in this particular equation. Okay, so we can actually calculate the lead time in this case in the same manner, assuming a 500 lot size as 500 times of time per component, and it comes out to be about 1264.37 minutes, okay, which is lower than the 1800 minutes total lead time obtained earlier. So this batch, because it is a maximum production rate model, will be getting quickly processed. The lead time is shorter by about 600 minutes in this particular case, and the optimum cost CU per component in this case again can be calculated by a similar formulation by just substituting the value of the cutting time, the minimum cutting time, a maximum cutting time in this particular case, which is 1.623 minutes. So I am just going to take the cost equation and just modify the time here to 1.623. Adding also the cost because of tool change, just simply substituting the different values corresponding to this particular TC value, and this comes out to be 4.81 or $4.82 per piece. So you can see here that because the production rate is the maximum or is at its maximum, the cost has increased quite a bit, because I think the tool cost here is contributing. So it's become about 4 times the cost per component in the minimum cost model, and so has the time changed significantly. The time has reduced because of the maximum production rate, and so logically whatever assumptions we are making are quite true in this particular case. So as you saw here, that there is a very clear cut demarcation of choosing the velocity conditions based on the maximum production rate or cost minimum cost models, where logically also they seem to be correct as far as the various comparative values, the numerical values go in both the situations. So I would like to end this module, and the computer assisted process planning would start from next module onwards. Thank you.